In this question number 8, we have a mixture of volatile organic compounds. Volatile means low boiling point, easy to boil. So X, Y, and Z can be separated in a gas chromatograph. This is a chromatogram because it's the result from the gas chromatography. This is what they call retention time. So how long do you spend passing through the column before you get to the detector, and you will have absorption once you reach the detector. So this takes the shortest time to pass through the column, so this doesn't stay in the column very long. Z is the slowest to pass out from the column, so Z spend the longest time in the column. So what is meant by retention time? So retention time is one of those things that you have to remember the definition of in the context of chromatography. And this is in the syllabus, obviously, chromatography. So this is the time taken by the substance to pass through the column. So you have a column to pass through the column inside the, during the chromatography. Okay. So we are having quite a long column to allow a better separation of these substances based on their ability to, how well they stick to the stationary phase, the phase that don't move at all in the chromatography setup. Okay, so we need to push along these volatile materials as well. So these are called carrier gas. So an example is one example. So usually we use things like helium. But then you could also use, what's the other one you use? Nitrogen, unreactive stuff. So helium or nitrogen, and they are typically used as the carrier gas. Now Z spends the longest time, so it has the highest retention time. So why does it stay the longest in the chromatographic column? Because Z probably has, what do we have in the chromatograph? Thing then we are not told about what is the stationary phase, so Z must have stronger affinity. Affinity means it has a stronger attraction, affinity or attraction to the stationary phase. Stationary phase is the phase that don't move at all, so it stays as stationary inside the column. And that is why it doesn't come up very quickly until you flush it again with the carrier gas, and it will come out the last one as it moves very, very slowly. Now explain a possible limitation in separating two esters. Now if they are both esters, they're going to have similar kind of intermolecular forces. They're going to have similar affinity for the stationary phase inside the column. And the fact that these are isomers, because you can see very clearly 1, 2, and 3 carbon, 1, 2, and 3 carbon. So they will not be very well separated, as they have similar kind of affinity or attraction to the stationary phase. They have the exact same mass, so they are not going to be separated very well. So these two esters are what you call position isomer, actually, because the second one is methyl ethanoate. So 1 carbon alcohol and 2 carbon acid, versus the other one, the first one I'm going to put on top there in red, that is methyl ethanoate. So 2 carbon alcohol, ethyl methanoate, 1 carbon carboxylic acid. So what's wrong with these two esters? These two esters are not functional group, position isomers. So position isomers come under structural isomerism. So you can say they are structural isomers as well. But what is interesting is that they both have similar intermolecular forces. If they have similar intermolecular forces, therefore similar affinity to the stationary phase inside the column. But not only that, they also have the same mass. They also have the same mass because they have the same molecular formula, since they are isomer. I already mentioned that earlier. So that will make them difficult to separate inside the column. Now student works out the area underneath the 3 peaks, because that is how you are going to interpret a gas chromatogram. So you are looking at the compound X. So you will have the area of compound X, which is 22, divided by the total area for all the component. And this one is multiplied by 100% because they're looking for percentage. So this is percentage of X, and you just have to press the calculator. So it's the ratio of the area of how much you have. So 22 plus 38 plus 16, that is 76. So 22 divided by 76 times 100, I get 28.9. But looking at how these are two significant figures or to the nearest whole number, I should really be thinking about rounding it up to the nearest whole number or two significant figure, just to be consistent with the data given in the question there. This next bit is all on NMR spectrum. This is a proton NMR. As you know, proton NMR runs from right to left, increasing that way. So the new 2022 syllabus onwards, the data booklet are no longer separated from the question paper. So if you are given an NMR question, you will have the data booklet at some pages, you know, whether in front or at the back of the question paper. You have an adsorption at this delta equal to 0 ppm. So this 0 ppm is your reference standard. Your reference standard has to be something which is easy to spot, and it has to be volatile, easy to remove. So easy to remove when you don't need it. It has to be unreactive, meaning to say you don't want it to react with your stuff, and therefore it will interfere with your result. And it's also very easy to spot, like because you have all of them having the same proton environment. It's actually called tetra-methyl silane. Okay, it's best if you know the name. It's called tetra because there are 4. Okay, tetra-methyl silane. So 4 of that methyl group, and around a silicon there is no hydrogen because all of them will replaced with CH3 there. Okay, I think I spelled the methyl incorrectly. Should be methyl like this. Nope, I had the wrong spelling. It should be the THYL, just like how we spell methanol, methyl there. I don't know what was wrong with me. Compound Y is an ester. So you have an ester, you have a 4-carbon ester. 4-carbon ester is your case study from chemistry. You should be able to think of ester like this. This is a 4-carbon ester where you have 1 carbon acid, and then you have 3 carbon alcohol. But because of this straight chain 3 carbon there, you could also have the potential for a branch isomer. It's called a chain isomer. That is also a 3 carbon alcohol. So 1, 2. And then our third isomer is going to be 2 and 2. So there's ethanoate. And then I have my ethanoate. 2 carbon acid, 2 carbon alcohol. And last but not least, I could also have my other one, which is 3 and also 1. When I say 3 and 1, I mean 3 carbon acid and 1 carbon alcohol. So this is methyl propanoate. This is ethyl ethanoate. This one is a branch group. They actually call this isopropyl. It's an isomer of propyl. So isopropyl methanoate. This is propyl. So this is propyl methanoate. We don't know which one is which one yet, but looking at these, you can see that there is a triplet. So a triplet would mean there are 2 neighboring protons, because 2 neighboring protons plus 1, 2 plus 1 give you 3 lines. So 3 lines, they are triplet. You see 4 lines there, which is a quartet. A quartet is 4 lines. That is because if you work backward, you must have n plus 1, which means you must have 3 neighboring protons. And last but not least, you have something between 3 and 4. You have 1 line, which is singlet, and singlet would mean 0 neighboring protons. 0 neighboring protons. Well, first of all, you got 1 signal, 2 signal, and 3 signal, 3 absorptions. And this thing is reference standard, so it's not the 4th one. 3 absorptions. Well, let's have a look at this particular structure. How many absorption are we thinking of? Well, you have one hydrogen there. I've circled in red, circled in black, 2, 3, and 4. So you have 4 different protons. You only had 3 absorptions in that NMR spectrum just now, 1, 2, and 3. If you have these, you will expect 1, 2, 3, and 4 because these are different protons. So meaning to say it cannot be number 1. So I can cross out number 1. Number 2, I would have 1, 2, and 3 because these and these are equivalent since you can rotate about these bonds. This CH3 and this CH3 are the same. But I can tell you it cannot be this because if you are this one, let's say if you are here, then you will see 1 neighboring protons. This and this will see 1 neighboring protons. Carbon from 4 bonds, 1, 2, and 3. If you are here, you see 1 neighboring protons. You will have 1 plus 1, which is 2 lines, which is a doublet. You will see a doublet. Well, again, if we look at here, we don't see anything that resemble a doublet at all. So what can we say? Cannot be number 2. So we are down to number 3 and number 4. Well, let's work out how many signal do we have here. We have 1, which is the CH3, 2, and 3. So you got 3 absorptions, which I can't decide yet. So let's have a look at the 4th one. How many absorption do we have? We have 1, 2, and 3 absorptions as well. So again, another 3 absorptions. Okay, what can help us? What can help us will be this thing here. If I just write this as, I don't know what other color is good. Let me use this color. This thing here is very important. The one I put an asterisk on. And this thing here is also very important. The one that I put an asterisk on. Put a double circle on it so that you can see they're very important. This is a CH3 next to carbonyl. In your data booklet or whatever data that you'll be provided with, this CH3 next to carbonyl, you expect it to be between, I think, let me just double check in the data booklet. I think it's 2.2 to 3.0. It could be wrong, but let me just double check. So CH3 next to carbonyl CO, you're looking at the second line in the current data booklet. Of course, you know, when you have the data booklet given an exam, it could be something different. So this will be a singlet because next to it is 0 neighboring protons. So you expect a singlet at 2.2 to 3.0 for this particular group there. Don't know why I did that. And now when you have this other one, you will have a CH3 next to electronegative oxygen. Directly, it is not next to carbonyl, it's next to electronegative oxygen. So here, when you are here, if the protons here, we'll see 0 neighboring protons. So it will still be a singlet. But where is this singlet? This singlet is next to electronegative oxygen. So alkyl next to electronegative atom. That is going to be 3.2 to 4.0 ppm. I think, having said that, you should be able to see where your singlet is. Your singlet here is between 3 to 4. It's not between 2 to 3. So there's no singlet here. There is a singlet between 3 to 4. So that would mean that it cannot be this one there. It cannot be number 3 structure, which means it has to be number 4. So they did say, use your conclusion to suggest a structure. I've already gone through the conclusion, so I can suggest the structure to be this one. If you don't like the skeletal formula, you can of course convert this to structural. It will be CO2 like this. I should probably write CO2, CH3. But of course, by doing things like this, you can see the CH3 next to electronegative oxygen. That's between 3.2 to 4.0. This is a CH3 next to electronegative oxygen. So they say electronegative atom. So this is CH3 next to electronegative oxygen. And what else? The 2.3, if we are here, I wonder what is what. So that is your 3.7. The 2.3 was a quartet. So the type of splitting, 2.3 was the quartet. And the 1.0 ppm was the triplet. So there was triplet. And this is the CH3 next to electronegative oxygen. So there was only 3 protons there. So there must be 3 hydrogens, 3 there. And we still have these 3 and 2. So when you are here, when you are at the very end there, you have 2 neighboring protons because there are 2 protons there. When you are here, you see 2 neighboring protons. So 2 plus 1 is 3 lines. You will get the triplet. So the 1.0 is actually for this thing at the end here. This thing is the triplet at 1.0 ppm. So you are a CH3 next to CH2. What I'm going to do is I underline where I am, and next to me is CH2. There is nothing on the other side. There are 3 protons. So you see 2 neighboring protons because this is where you are. Now to the next one, you are talking about here. So you have to think about, because you are in the middle, we have to show the CH2 in the middle is next to not only alkyl but next to C double bond O, and that is the reason why it's no longer the 0.9 to 1.7. It's a bit higher, between 2.2 to 3.0. Alkyl next to carbonyl, alkyl next to CO carbonyl. You have 2 protons there. You don't couple to the protons there, but you see 3 neighboring protons. So 3 plus 1 give you 4 lines, which is quartet there. So hopefully that kind of settled the idea of the 4 different possible isomers containing 4 carbons, 4 esters. But of course, looking at the number of NMR signal, it cannot be the other one. And by comparing the CH3 bonded to CO, which will give you a singlet there, versus a CH3 bonded to oxygen directly, which will give you a singlet at this position, you should be able to tell which isomer is represented by this particular NMR spectrum there. And that's it really for this 11 mark NMR question.